In today's lecture, I'm going to move to the next chapter on applications to optimization. And in the first section, I'm going to discuss the lower semi-continuity and existence of minimizers for optimization problems. As you know, if we have a continuous function, then it attains its absolute minimum on any complex set of Rn. In fact, when we study minimization problems, we only need a less restrictive assumption on the function. So instead of requiring the continuity of the function, we only need the lower semi-continuity. So now I'm going to go into the detail of a lower semi-continuity and prove a result on existence of minimizers. Let f from Rn to the extended real line be a function. So over here, we do not assume the convexity of f. Okay, so we say that f is lower semi-continuous or LSC for short at x bar if for any lambda that is strictly less than f of x bar, there exists delta greater than 0 such that lambda is less than f of x for all x in the ball with center at x bar and radius delta. Okay, so this condition means that if lambda is less than f of x bar, then we can find a neighborhood of x bar so that this property is still satisfied on that neighborhood. Okay, so if lambda is strictly less than f of x bar, then we can find a neighborhood of x bar so that lambda is less than f of x for all x in this neighborhood. Okay, and here is an example. Now consider the function given by f of x is x squared if x is not 0, and minus 1 if x is equal to 0. So here is the graph of the function. Okay, so as we know, this function is not continuous at 0. Okay, however, it is lower semi-continuous at 0. So to see why the function is lower semi-continuous at 0, we take any lambda that is strictly less than f of 0. In this situation is equal to minus 1. Okay, so lambda is less than minus 1. Okay, now from here you can see that if we take this neighborhood of 0, say minus 1, 1, then within this neighborhood, as you can see here, f of x is greater than lambda. In this situation, for all x in this neighborhood of 0. Okay, so if we take any lambda that is less than minus 1, then you can find a neighborhood of 0 so that within that neighborhood the function values are greater than lambda. Okay, so the function f is lower semi-continuous at 0, and from there you can also see that f is lower semi-continuous at any point of in R. Okay, and this is another example. If we consider the function g given by g of x is x squared if x is not 0, and 1 if x is equal to 0. So in this situation, f of 0 is equal to 1. Okay. Now, how come this function is not lower semi-continuous at 0? If we take some lambda, for example, lambda here is equal to 1/2. So lambda is less than f0, which is 1. So lambda is equal to 1/2, and it's strictly less than 3 of 0 actually. But if we take any neighborhood of 0, if we take any neighborhood v of 0, we can see that there are points at which the function values are less than 1/2, as you can see from this figure. Therefore, G is not lower semi-continuous at 0. Okay, so in this definition, if f is a lower semi-continuous at all x bar in Rn, then we say that f is lower semi-continuous. Okay, so f is lower semi-continuous if it is continuous at every point of Rn. Now I'm going to discuss further properties of lower semi-continuous functions. In the next proposition, we're going to see some links between lower semi-continuity and the continuity. Let f from Rn to the extended real line be a function, and let x bar be a point in the domain of the function. Then f is lower semi-continuous at x bar if and only if for any epsilon greater than 0 there exists delta greater than 0 such that f of x bar minus epsilon is less than f of x for all x in the ball with center at x bar and radius delta. Okay, so in this proposition, we require an additional assumption compared with the definition of lower semi-continuity. So over here, we require that x bar is in the domain of the function. That means f of x bar is a real number. Okay, so in this situation, we will see that this is very similar to the definition of continuity of a function. Okay, so in the definition of the continuity, we require that the absolute value of f of x minus f of x bar is less than epsilon whenever x is in this ball. Okay, and this inequality can be written as f of x minus f of x bar is in between epsilon and minus epsilon. Okay, or it can be written equivalently as f of x is in between f of x bar plus epsilon and f of x bar minus epsilon. Okay, but in the definition of lower semi-continuity, we do not need this part. Okay, but we require this condition. Okay, so and similarly later on we can also define upper semi-continuity using the second part in this inequality. Okay, so now I'm going to go ahead and give the detailed proof of this proposition. In the first direction, I'm going to assume that f is lower semi-continuous at x bar and then prove this. So suppose that f is lower semi-continuous at x bar. Now take any epsilon greater than 0. Then the number given by f of x bar minus epsilon is strictly less than f of x bar. Okay? So by the definition of lower semi-continuity, because lambda is strictly less than f of x bar, we can find a neighborhood of x bar on which this property is still satisfied. That means there exists delta greater than 0 such that lambda, which is f of x bar minus epsilon, is less than f of x for all x in this ball. Okay? So we have seen that if we take any epsilon greater than 0, then there exists delta greater than 0, so that this is true for all x in this ball. Okay? So we have proved the first direction. That means if f is lower semi-continuous at x bar, then this is true. Okay? Now let me go ahead and prove the converse. Suppose that for any epsilon greater than 0, there exists delta greater than 0 such that this property is satisfied for all x in the ball with center at x bar and radius delta. Our goal is to show that f is lower semi-continuous at x bar. So to prove the lower semi-continuity of the function at x bar, we're gonna apply the definition. Okay? So take any lambda that is strictly less than f of x bar. Okay? So then we can choose epsilon greater than 0 sufficiently small such that lambda is less than f of x bar minus epsilon. Okay? Because lambda is a number that is strictly less than f of x bar, we can always choose epsilon so that this is true. For example, you can take epsilon to be f of x bar minus lambda. Okay. Now, by what we have from the hypothesis, then there exists delta greater than 0 such that f of x bar minus epsilon is less than f of x for all x in the ball with center at x bar and radius delta. But we know that f of x bar minus epsilon is greater than lambda. So from here we see that f of x is greater than lambda for all x in this neighborhood. So by the definition, f is lower semi-continuous at x bar. Okay, one important remark: if we do not require the hypothesis that x bar is in the domain of the function f, this property is no longer valid we can find a counterexample for that. For a function f, the lower level set L lambda is given by the set of all x, so that f of x is less than or equal to lambda. Like in this figure, this is the graph of the function y equals f of x, and this is lambda. So this is the set L lambda. Okay. In the next proposition, we're going to see that a function f is lower semi-continuous if and only if L lambda is closed for every lambda in R. Okay. So this is a very, very nice characterization for lower semi-continuity. Let f from Rn to the extended real line be a function then f is lower semi-continuous if and only if for any lambda in R, the set L lambda given by all x in Rn such that f of x is less than or equal to lambda. The set L lambda is closed. And as you know, L lambda can be written as the pre-image of minus infinity to lambda. Okay? It is well known that a function f is continuous if and only if the pre-image of any open set is open. Equivalently, the pre-image of any closed set is closed. But for lower semi-continuity, we only require that the pre-image of any closed set of this form is closed. Okay? So let me go ahead and give the detailed proof of this proposition. In the first direction, we suppose that f is lower semi-continuous. That is, f is lower semi-continuous at any point of Rn. Okay. Now fix any lambda in R. Let us show that the set L lambda is closed. Okay. So to show that L lambda is closed, we're going to show that its complement is open. Okay. So take any x bar that is in the complement of L lambda. Okay. By the definition, lambda is strictly less than f of x bar. Okay. As we know, x bar belongs to the lower level set if and only if f of x bar is less than or equal to lambda. So x bar is not in the lower level set if and only if this inequality is not satisfied, that is f of x bar is greater than lambda. Okay. Now because f is lower semi-continuous, it's lower semi-continuous at x bar. Okay. Because f is lower semi-continuous at x bar. Now f of x bar is greater than lambda, so there exists delta greater than 0 such that this property is still satisfied within a neighborhood of x bar. So lambda is less than f of x for all x in the ball with center at x bar and radius delta. So because lambda is less than f of x, we see that x is not in L of lambda. Okay, so we see that the ball with center at x bar and radius delta is a subset of the complement of L lambda. Okay, because again, if you take x in this ball, you see that f of x is greater than lambda. So x is not in the lower level set. Okay, so now to summarize, we take any x bar in the complement of L lambda, and then we can find a ball with center at x bar and radius delta, so that this ball is a subset of the complement of L lambda. Therefore, L lambda, the complement of L lambda, is open, and so L lambda is closed. We have completed the proof that if F is LSC, then for any lambda in R, the lower level set L lambda is closed. Now, I'm going to go ahead and prove the converse. For the converse, we suppose that L lambda is closed for all lambda in R. We will show that F is lower semi-continuous. Okay, now take any x bar in Rn and lambda strictly less than f of x bar. Again, we will show that there is a neighborhood of x bar such that this property is satisfied in that neighborhood. Okay, so now consider the set L lambda. Again, is given by all x in Rn, so that f of x is less than or equal to lambda. Now, because f of x bar is greater than lambda, x bar is not in this lower level set, then x bar does not belong to L lambda. So x bar again is in the complement of L lambda. Now, as we know, L lambda is closed, so its complement is open. So we can find a neighborhood of x bar so that this property is satisfied. So there exists delta greater than 0 such that the ball with center at x bar and radius delta is a subset of the complement of L lambda. Again, this is true because this set is open. Now, what does it mean by this? So, if you take any x in this ball, x is in the complement of L lambda. That means x is not in L lambda. So, f of x has to be greater than lambda. That means f of x or lambda is strictly less than f of x for all x in the ball with center at x bar and radius delta. So we have seen that if you take any lambda that is strictly less than f of x bar, then you find a neighborhood of x bar on which lambda is less than f of x. Therefore, by the definition, f is lower semi-continuous at x bar. So the proof of the proposition is complete.